students. So continuing the lecture, next we will be studying about the balancing of locomotives. So I told you already that there are two types of locomotives, coupled and uncoupled. What happens in coupled locomotive is unbalanced masses can be considered as revolving mass and can be completely balanced. So whatever unbalanced mass we have, they are only considered as revolving mass about some point. Now here in uncoupled locomotives, we have to consider uh, different planes. The number of planes for consideration of unbalanced masses are separate. So in one plane, one unbalanced mass is present. Next one plane, another unbalanced mass is present. Okay, both revolving and reciprocating unbalanced masses are present. Now, in coupled locomotives, mass required to balance the reciprocating mass parts is distributed among all the wheels. So here, uh, in a coupled locomotive, you see reciprocating parts. Okay, since you can say that the wheels are you're rotating, right? So you see there will be some reciprocating. In locomotives, you have seen that this is one wheel, another wheel, wheels like this. Then we have a connecting rod here. Okay, and then we have a crank here. We have a piston here. This type of arrangement you have seen in your steam locomotives, right? So there we have your unbalanced reciprocating parts. Now there is something called hammer blow. Now what is hammer blow? It is the maximum vertical force which is unbalanced. Its value is mr omega square. Just like here that we have seen that this is the mr omega square force here, okay, and it has a horizontal component and a vertical component. So in this case, similar to mr omega square cos theta and sin theta, we have a vertical force. Suppose entire locomotive will consider this as reciprocating and rotating parts. Here we have one vertical unbalance. Okay, suppose this is one wheel, another wheel, another wheel. Wherever we have everything connected, okay, we have a vertical, okay, motion like this. Okay, like this, up and down, up and down. So this is called hammer blow. And this is an unbalanced force, and the value is mr omega square. So this is caused by the mass provided to balance the reciprocating mass. Okay. So sometimes you know that the reciprocating unbalance is there. So if they provide some mass to balance that, and that mass additionally causes some up and down motion, vertical up and down motion. That's called hammer flow. Next is variation of tractive force. Now this tractive force. Okay. Now you see, for any engine, for a vehicle, three-wheeler, four-wheeler, two-wheeler, or train, etc. This is the track, and here we have the wheel. So whatever force is needed to move the train along the track. So this is track. For four-wheelers, the track will be the road. Okay. So what is the force that is required? You see, if you apply a less amount of force, it may not go forward or backward. Okay, so a sufficient amount of force must be provided by using the engine or motor, whatever you have, using that external the power source. You have to provide some sufficient amount of force, then only it will start moving, and that force is called tractive force. Okay? Tractive force generally comes into call it, specifically called tractive force when it is associated with uh, your trains, okay, then vehicles, etc. When something moves in road, okay, in some track, okay, this is called tractive force. Force required to move the your vehicle in the track. Now variation of tractive force. We'll talk about the variation or effort given by the engine is caused by unbalanced portion of primary force which acts along the line of stroke. Now it's difficult to show that the engine. But let me draw the engine. So suppose this is the engine side view. Okay, you assume this is the one of the wheel, another wheel, another wheel. Okay, more wheels are there. So here we have the connection. Okay, so the train is moving, locomotive is moving in this direction. All right, and what we do is we take the engine like this. You see, in a steam engine, you have seen that uh, uh, this engine part, okay, where the steam presses your steam actually releases at this type of horizontal engine, okay, where piston is there and piston moves to and fro horizontally, okay, this type of motion. So this moves like this, and the connecting rod moves the wheels, okay, that is how it goes. So you see the engine stroke in this case is horizontal, either in this direction, this direction. Okay, horizontal engine stroke. So along the line of stroke, we have the primary force, unbalanced force. Okay, so the train here, or the locomotive here, uh, train will be when we connect all the radius is also. We are talking about the locomotive. Okay. So here, what happens is see. So forward stroke, it may have a higher amount of some stroke. Then return stroke is there. Okay, this will oppose the movement. So what happens is there is a variation of tractive force. Tractive force is a constant force that tries to move the whole thing forward, but because of the to and fro motion of this piston, okay, there may be variation in the tractive force. Tractive force increases, then it will decrease. Okay, then increases, then decreases. The movement will be like this intermittent movement. So in that case, we will have an unbalance. Okay. So unbalanced portion of primary force, some, by the way, primary force mr omega square, okay, it's some portion of that force will cause the unbalance. By the way, I'm sorry, mr omega square will come from actually the rotating part, huh? And for reciprocating part, the primary forces, oh sorry, yeah, this is actually, this causes the reciprocating unbalance, yes, and some portion of that causes variation in tactic force. Next is, since we cannot just balance completely the primary force, we have to balance a portion of it, a fraction, okay, percentage of that. So let's take the c, small c is the percentage or fraction of the reciprocating mass that we can balance, okay, and we actually that variation of tractive force, see, we can just say that tractive force is, let's say minimum tractive force is 50, suppose, okay, 50 newton, and it goes to 100 newton, okay, then it again reduces to 50 newton, then it again goes to 100 newton. So because of that, the intermittent movement is there, okay. So you can say that the maximum value of is this, minimum value of this. So from minimum to maximum or maximum to minimum, this is called the variation, okay. So the maximum variation in this case will be the maximum difference between or you can say the difference between maximum and minimum values. So that is given by this formula. Okay. This one, plus minus, plus when it is increasing, minus when it is decreasing. Okay, plus minus root 2 1 minus c mr omega square. Okay, so it depends upon how much amount of what is the portion of mass that you have balanced. Okay, so then 1 minus c multiplied by mr omega square. See, c is the portion balanced, and whatever remains unbalanced, okay, that is 1 minus c. That is actually, I told you in the previous video that the c is the balanced portion. That is, c is suppose some percentage, 50%, 60%. Then c value will be, if 60%, c will be 0.6. If 50% is the fraction, then c will be 0.5. It's like that. So suppose you have balanced 50% of the mass, so 50% remains there. Okay, 50% is yet to be balanced. So in that case, 1 minus c gives you the unbalanced portion of that. Okay. So 1 minus c multiplied by this force is the unbalanced force, multiplied by root 2, and we have this plus, that is a maximum increasing of the active force, and minus, that is a maximum decrement of tractive force. So this is how we give the variation of tractive force. Okay, that is also an unbalance. Next is swaying couple. Now swaying. Okay, now for that, let me show you the front side of the locomotive. So you just think that this is a locomotive, huh? And we have some windows there. Okay, windows there. By the way, in old locomotives there were no windows, but just think that for your understanding, you are facing the locomotive here. You're standing and your locomotive is coming towards you. So this is the track. Okay, I hope you understand these are the sleepers. So the track is towards you. Okay, understand this, I think. Okay, so this is the track. So now let's show the wheels. So this is one wheel, right? This is the wheel. This is another wheel, locomotive wheel. Okay, so these two wheels are there, and the engine is normally, we just, for your calculation purpose, we have placed it in between them, in between them. So this is horizontal engine. The stroke is horizontal. We are actually looking at the front view. If you look from this side, okay, let's just show it from this side, the side view of this side, okay, then it will look like this. Okay, one wheel, another wheel. So whatever amount of, how many wheels are there, we'll show them. Then we have this connecting rod, etc. So the engine is here. Okay, we have shown. And this is horizontal. It is giving a horizontal stroke. Horizontal stroke. Right. So now you see that. So what's happening here is some kind of horizontal stroke you are giving here. Okay, and you're in we are looking at this, what's going on here. Let's see that. Now we have something called swaying couple. Okay, it is called the unbalanced primary forces which are separated at a distance L apart constitute a couple. This tends to sway the leading wheels, okay, side to side. Now the thing is, you see, this type of motion, okay, causes these two wheels, these two leading wheel means the frontmost wheels, we there is a tendency of separation of the wheels apart from each other, okay, because of a couple. Now what kind of couple is that? That is called swaying couple. Now if you look from the top, okay, then we are showing the engine stroke here, stroke, it's the forward stroke, okay, and you see these are the unbalanced portion of the forces, unbalanced portion. This is one unbalanced portion of the reciprocating force. Okay, so mr omega square multiplied by 1 minus c is the unbalanced force that remains there. Okay, now this this is cos theta. Okay, that is the horizontal component of this. Okay, and here we have 90 plus theta. Actually, this is actually perpendicular to this one. Okay, because this is 90-degree added to this one. Okay, the angle. So this is perpendicular to that one. So what we have here, you can see that we have two unbalanced forces, okay, which causes resistance, or you can say which is, this is the direction of the stroke, suppose in this stroke, and these are the directions of the couple. Okay, so so not the couple, the unbalanced force. So you can see that this part, this one and this one, they cause a couple like this. Okay, rotation. Okay, let me show it again. So this type of couple is caused, isn't it? See, this is going in this direction, this is going in this direction. This kind of rotation is caused by this. And considering this one and this one, we have a couple like this. Okay. So what they cause is, if we can see clearly, this part is going to push the wheels away from each other. That is what we have here. This is the wheel, this is the wheel. Okay, this is going to push the wheel in this direction, push the wheel in this direction. It's called swaying. That part is called swaying. So you have seen in vehicles, if you have not seen, you can see, you can search in your internet that there is one bar, okay, some kind of rod is there in your four-wheeler nowadays, okay. So previously, so they had this one that is called sway bar, SWAY, sway bar. So sway bar actually stabilizes the vehicle, okay. Because of this kind of swaying motion may occur at the leading wheels may they tend to separate each side, okay, side to side. So that causes some what sideways movement, sideways unbalance like this, okay, this kind of movement. So you can see that how many movement hammer of vertical unbalance is there, radiation of tractive force, that is one, and sideways movement is there. It is the swaying couple. Okay, so we have to balance all of them. Okay, so here we actually will talk about these three only, and the balancing is a little bit complex in this case. So we will not discuss that part. Okay, and later on, okay, some concepts I'll clear it in your class. So the thing is, here we can see that the swaying couple is given by this formula. Okay, so after derivation, we will obtain such type of formula. Here you can see 1 minus m 1 minus c mr omega square is the unbalanced force. Okay, multiplied by L will give you a couple. Okay, because the length from here to here we've assumed this engine is in between them. So the gap between these two we have assumed as L. So one of them here will be taken to this position. So if you have to take this force to here, you can multiply with L. You know that. So this is the swaying couple value. Okay, divided by root 2. So plus minus the whole thing gives a value called swaying couple. Right? So this is called swaying couple. So we have learned about these three things: MR blow, horizontal force, and swaying couple. Next, let's look at some numerics. The following data refer to a two-cylinder uncoupled locomotive. Okay. So here rotating mass per cylinder is 280 kg, reciprocating mass per cylinder is 300 kg. Both rotating and reciprocating mass values are given. Okay. Distance between wheels, okay, 1400 mm. So one wheel is here, another wheel is here. That distance between them is 1400. Distance between cylinder centers. So here we have more than one cylinder. Yes, two cylinders given. So distance between cylinder centers, so center lines. So suppose one engine is there, another engine is there. Between that, particularly if you see, the gap is 600. Okay, 600 mm. Then crank radius is given 300 mm. Radius of center of unbalanced mass is 620 mm. Okay, so unbalanced mass is somewhere, it is reciprocate rotating about some point, so that radius is given. Unbalanced mass we have to find out. Okay, and but the radius is given at 620 mm. This is unbalanced. Our locomotive speed is 50 km per hour. Okay, then angle between cylinder cranks is 90°. Diameter of treads of driving wheel 1800. Okay, so this is actually okay. So this is the diameter of the wheels actually. Diameter of the wheels. So now determine the balancing mass required in the planes of driving wheels if whole of the revolving and two-thirds of the reciprocating mass are to be balanced. In the swaying couple, then variation of tractive force. So what you have to find? You have to find a balancing mass, swaying couple, and variation of tractive force using these data. So let's have a look. So if the diagram is not given, you have to see what you have to do is you can see that this is one wheel right here. There is some engine here, okay, and this is one wheel. In this particular problem, we have two cylinder means two engine. So instead of having this, we'll have one wheel, one engine, okay, next another engine, next another wheel, okay, like that. So 1, 2, 3, 4. that we will show it in a line, in this kind of line, so that we can solve it easily. So this one is a wheel. Okay, wheel, first wheel. This is another wheel at point 4, and 2 and 3, these are actually engines. Okay, so we will first make 1 2 3 4. Okay, we know the see gap, the distance between cylinders and is 600 mm. So these are cylinders 2 and 3. Cylinders means engine only. Gap between them is 600 given to you, so just mark 600 here. Okay, so then again, what is given, what else is given? You can see that distance between wheels. So this one is another, this is the I mean first wheel, this is second wheel. So gap between them is 1400 mm, so we have shown it this 1400 mm. So anything else? Okay. Distance between cylinders, crank radius 300, radius of center of unbalanced mass 620. So it's 400. I think that I missed it in the question, but this part, gap between the first, I mean the reference plane is taken at the first wheel. Okay, gap between reference plane and first engine or first cylinder is 400 mm. This is given. Okay, this is given in the question. So if in a question in your exam some data is missed, you can suitably assume it. Okay, so here this is actually given the question that is not written here. So 400 mm is it. So here you have converted it to, see I told you in the uncoupled locomotives, you can see that in uncoupled locomotives, where is it, number of planes for consideration of unbalanced masses are separate. So different planes for unbalanced masses are to be considered. This is one plane, another plane, another plane, another plane. 4 planes are considered. So first plane is the reference plane we take here. Okay, this is angle theta 1, this is angle theta 4. We can, I mean, just take theta 1, theta 2. Now see one thing, one extra information is given. Angle between cylinder cranks is 90 degrees. So if one crank is horizontal, next one will be vertical. If this one is vertical, this will be horizontal, because their engine crank angle, difference between their angle. So suppose this crank is suppose going to TDC, next one will go to at the middle point, not BDC, here. Okay, because of that what actually, let me show you in this manner. Suppose it's an IC engine, suppose, then this is one cider crank. Okay, so this crank is here. Okay, next one, if it is, this is the position for the first cylinder, next one the crank will be here. Okay, because then only the gap between these two is 90 degrees. See, this is the crank, no, this one is the crank, this portion, the crank, this is the crank. Okay, so the crank one for the first one is here, and next one is here. So if we take this one here, so the gap between them is 90 degree. Okay, so you can take one of them as 90, next one will be 180. If you take one of them as 0 degree, next one will be 90 degree. That's why we have taken this as 0 degree and this one is 90 degree. Okay, so we are given with the angles already. So if you take this 0, this will be 90. If you take this 90, this will be 180. Okay, so one will be 90 degree ahead of the next. Okay, that is given in the question. Now you know that we have learned this previously, that for both reciprocating and rotating masses, the total mass that is to be balanced, okay, that we need to balance, can be found from this formula. Okay, so the portion, the percentage is actually, in this case percentage is not given. C value is given as 2/3 of reciprocating mass to balance. That means C is 2 by 3. C is 2 by 3. Okay, and the reciprocating mass is 300 kg given, plus the rotating mass 20. So using this formula Cm plus Mp, you have to find out total mass to be balanced. Okay, So to be balanced, there must be balanced Cm plus m. C value is 2 by 3 given, m is the reciprocating mass plus rotating mass. So this is the total mass 40 kg. We need to balance it. Now rest of the problem is what? Just use the concept of your uh, balancing of rotating masses. So here you see, take this as a reference plane. How to solve it? Using the first equation, that is your when you take this as reference plane, take this force here, this force here, this force here. All three, if you take here, they will form what? Couple. And we have to multiply the lengths. So if you take this one, suppose there is a mass m2, m3 here, m4 here. So m2 r2, radius is r2, m2 r2, the distance is l2, angle is theta 2. So we'll just write that m2 r2 l2 theta 2. See, m1 r1 l1, l1 is 0, so we don't write that thing. Okay, m1 is there, r1 is there, l1 is equal to 0 because it is in the reference plane only. Exactly, there is no gap between 1 and the mass is there itself in the reference plane. So the gap, axial gap is 0. That's why we don't write it. M1, M2, R1 is not written. Okay, if you want to write, that's okay, but the length is 0. In this case, L2 is 400. Okay, L3 will be what? 400 plus 600. Okay, that means L3 is the gap from reference plane to M3, mass at 3, and M4 is the so gap. L4 will be the gap between reference plane to this mass at 4. That is 1400. So M3, L3, we have written this. M4, R4, L4, we have written this. Okay. So ultimately, we know the values here. So let's find out. In this case, we don't know this angle theta 4. Okay. So we'll just keep it aside like this. Okay. So we have found that we also don't know the value of M4 here. Okay. That we need to balance. Actually, you can say that this is the balance force. Yeah, balance mass, and these are unbalanced masses, engines. Okay, so we'll just using that horizontal component form, horizontal component equation, we have found m4 cos theta 4 is equal to this. Similarly, by finding out the vertical components of these forces, we have found m4 sin theta 4 is this. Okay, just write m2 r2 l2, m3 r2 l3, all the values are given. See, R2 and R2 is given 300, R3 is also given 300. Why? Because you see crank radius. Okay, crank radius is 300. So this is the engine. Okay, engine mass is somewhere, no? So this is the mass and this is the crank radius. So this part is revolving, right? Like this. So the crank radius is 300. That's why R2 is also 300. R3 is also 300. But R4 is given here. You see this one, radius of center of balanced mass. So here this is the balanced mass, right? Balanced mass. So this radius is given. Okay, this is 620 is given in the question. So that's why this is 620. Okay, so here we have written this LR4 as 620. Okay, clear? So by putting all the values, we have got two equations: M4 cos theta 4, M4 sin theta 4. Using solving these two, squaring and adding, we can get M4. This is the value 178.7 will be the mass here at 620 mm distance. That will balance at 0.4. We are still left with this mass. Okay, M1. We'll find it out. Now we have found M4 and the angle. Angle you know how to find just by dividing this by this one. Okay, we have found the angle as 68.19 degree. Now this is actually the unbalanced force. Okay, I told you these are actually what is that? This is actually the unbalanced mass. We have to balance it by providing another counter mass at 180 degree or exactly opposite to that. That's why we have to add 180 degree to this. So 248.19 degree will be the total angle here. Okay, actually the mass 68 point, this will be here. Okay, so to provide an equal and opposite force to this, so we will provide an mass M4 at a distance of 620 mm and at an angle of 268 with horizontal at 248. Now, how to find out m1 and theta 1? So now take the other one as reference plane. This part is reference plane. This is a little bit different. Okay, so you have to take this as reference plane now. Take this as RP and do the same thing. Now you transfer this here. Transfer this here. Okay, transfer this here. So you have to just transfer all of them and then you solve. You know how to transfer it, right? Just by multiplying m2 r2 l2 cos theta 2. Now the thing is, what will be l2 now? You see, for this one, 2, distance between 2 and 4. Okay, this is the distance. What is the distance? 1400 minus 600 plus 4. 1400 minus 600 plus 4. 400. That will be 1000, right? So 1000, this gap is 400. We have found this as 400. So the total distance between 2 and 4 is 600 plus 400. That is 1000. So here you can see this is 1000. Okay. See, previously it was 400. Now it is 1000 because we have changed the reference plane. So this is L2. R2 is 300, you know. R2 is 300, you know. R1 is 620. That is again because of the what is that? Radius of center of balance mass. This is same for the balance mass here also. Okay, 620 mm. So you have seen that this is 620 mm, this is 300, this is 300. L2 is 1000. L3 will be what? L3 will be the gap between 3 and 4, which is 400 mm. You can see here 400. Okay. M3 is known, M2 is known. These are given actually. 480. Now one more thing. Why 480? Because we have found out actually this part. We have combined the reciprocating and rotating parts together. So actually it's about when you solve the numerical, you actually combine reciprocating plus rotating using this formula. Then you start solving. Okay. 480 kg is the total mass of this engine and remains unbalanced. This engine also remains unbalanced. 40 kg, 40 kg. That's why M2 and M3 both are 480 kg. M2 and M3 480 kg. M1 is actually unknown, so we'll write it as it is. And 620 is that is given the question. And L1 now will be the gap between 1 and 4. That is 1400. So we have done this 1400. Okay, 1400 cos theta 1. So by solving with the previous equation, we have got the same 178.7. Here also we have got the 178.7 only, but the angle is different now, 21.80. And since we have to provide a balanced mass at 180 degree apart from this, we have to add 180 degree to it. So this is the exact angle, 201 degree. So we have to place your mass M1 at 201 degree here. Okay, this angle will be 201 degree. So M1 value is 178.7 and the radius is 620 given in the question. So we have found both the balance masses. Okay, so balance mass, okay, by balancing 2/3 of reciprocating mass. The first question answer is done. Next two part can be found using the formulas. Okay, use this formula to find and to find the variation of tractive force and use this formula to find out the swaying couple. So here you see we need to find out omega because in the formula omega is there. So see velocity equal to r omega, you know, omega will be v by r. Velocity is given, okay, linear velocity 50 km/h and rpm is also given somewhere. Where is it? Not, sorry, rpm is not required if you know the radius of the crank radius. So from here you see, oh, I'm sorry, not the crank radius, here diameter of the wheel is required. Wheel. Oh. See, the thing is, this is the locomotive, no? Locomotive. This is the wheel. Okay. Locomotive is linear velocity is given 50. Okay. So to find the angular velocity of the wheel omega, okay, we have to take its radius of the wheel, okay, and the velocity of the entire thing. So linear velocity of this wheel is known, that is 50 km/h. Radius is given because the diameter is 1800, so radius will be 1800 by 2. Okay, so here you see This radius is 1800 by 2, that is the diameter by 2, and this 50 kilometer per hour we have converted it to meter per second. So we have got the ultimately omega is 15.43 radian per second. So just by putting the value of omega here and this mass here 300, r is 0.3, okay, l is 0.6, right? So by the way, what is l? Why l is 0.6? Because let's go back to the question here again. Distance between cylinder centers. Okay, so this is actually let's go back to this one, this part. We are talking about this one L. So here this unbalanced force and this unbalanced force causes the couple. So we have to take one each from here to here. Okay, so this is 600 given in the question, that there are gap between what is it, distance between cylinder centers, these are between unbalanced one, unbalanced, this is causing a couple, this is causing a couple, sorry, both of them causing the couple. So here we have 600 is a gap between them, so we have to take the length L as 600 or 0.6 meter. So C value is given, so we can find out a swaying couple from using this formula. M is 300. Now why M is 300? Again, let's go back to this one. So reciprocating part. Okay. So swaying couple is called by reciprocating part, isn't it? Here you can see unbalanced primary forces, which are actually this considers a couple because of the reciprocating parts. These are reciprocating unbalanced forces. So that's why here you can see that this mass will be reciprocating mass only, not the total mass. Reciprocating mass per cylinder. So reciprocating mass is 300. So here I have to take that 300 here. 300. So 300 radius is 0.3, 300 radius again. Why? Because this is crank radius. Crank radius is 300 Okay. That's why we have considered only the engine here. Swaying couple is caused by the engine. So here gap between the engines is 600 Okay. So M is 300. Okay. Then this radius is 300 mass is 300 kg. M radius is 300 L is 600 and omega we have just found by putting the values. We have got the swaying couple and the variation of reactive force. This is the formula, plus minus root 2 1 minus C mr omega square. We know all the values, isn't it? Just put C equal to 2 by 3. 2 by 3 is given in the question. So M is 300, you know, R is 300 you know, and omega is 15.43. Just by putting it, we have got the variation in reactive force. So 10100. So this completes the numerical, and we will stop here.